Section 7.3, Volume using solids of revolution, the shell method. Now, the shell method is an alternative method for finding the volume of a solid of revolution. In the shell method, instead of our rectangles being perpendicular to the axis of rotation, we're going to make our rectangles parallel. So, for example, in this region here on the right-hand side of the y-axis, if we were to revolve this region around the y-axis, it would actually take us two separate integrals to be able to find the volume. You would need a disk for the lower half, and you would need a washer for the upper half. Now, that is completely fine. You can find the volume that way. However, if we could change the direction of the rectangles and turn them so that they are vertical instead of horizontal, then we will be able to calculate our volume using one integral instead of two. So once again, the rectangles must be parallel to the axis of rotation. Now, what ends up happening is if we take our rectangle and we revolve it around the y-axis, we end up generating some nesting shells. So you're going to have one rectangle being concentrically inside of another one as we develop the volume. So if we take the shell and we kind of separate it out, if I take the shell here and trim it up the side edge and lay it out flat, we would then have a rectangle with just a little bit of height to it. So what I know is that this piece is going to be the height of the rectangle. This piece from here to here is actually going to be the circumference of the cylinder. So this is going to be 2 pi r, the circumference of a circle. And then the thickness, which is this little thin part right here, that thickness is either going to be the change in the x or the change in the y. So the volume of this really thin rectangle is going to be V equals 2 pi r times the height of the rectangle times the thickness. So once again, the r is going to be the radius or the distance the rectangle is away from the axis of rotation. The h is going to be the height of the rectangle, and the thickness is either going to be your dx or your dy, depending on what direction the rectangle is. Now remember that vertical rectangles, we're going to be working with x's, so we need our equations in terms of y and have dx in the integral. For horizontal rectangles, we need everything in terms of y, so we're going to have our equations in x equals form, and then dy is inside of the integral. Now, once we get the volume of one cylindrical shell, then we simply accumulate them. So, accumulating, we get the equation that the volume is going to be 2 pi times the integral from a to b of the radius, which once again is the distance from the axis of rotation to the rectangle, times the height, which is the height of the rectangle, times the thickness, which is either your dx or your dy. So let's try one of these. Now, once again, the volume is going to be 2 pi times the integral from a to b of r times h times the thickness. Now, in this problem, if we take the parabola y equals x squared plus 1, the line y equals x plus 3, so only the portion that has x greater than or equal to 0, and we revolve it around the y-axis. So this is actually the same picture that I had on the front page, but now we have equations to work with it. So if we are going to use a shell method, so we only have to set up one integral, that means that the rectangles must be parallel. Parallel means that they will be vertical. Since they're vertical, that means that our thickness is going to be in terms of x's. So our volume is going to be 2 pi times the integral from, for the x's are going to range from 0 to 2, so the integral from 0 to 2 of the radius times the height. Now, once again, the radius is the distance from the axis of rotation, that's the y-axis, the axis of rotation to the rectangle. That distance is a distance of x. So the radius, or the distance away from the axis of rotation, is a changing variable distance of x. Now, the height of the rectangle, this is actually going to look very familiar. We found the height of the rectangle when we calculated the area back in section 1. The height of the rectangle is going to be the top function minus the bottom function. So the top function is going to be the line, the bottom function is going to be the parabola. So we are going to take the top function, which is x plus 3, minus the bottom function, which is our parabola x squared plus 1 dx. So our volume is 2 pi times the integral from 0 to 2 of x times x plus 3 minus x squared minus 1, if we distribute the negative, dx. Now, just like on the other sections that we've talked about so far, the setup is going to be the more important piece. Once you get it set up, at this point you can then go to the calculator and ask it to give you the solution. Let's try another one. This one, we're going to take the half parabola laying on its side, square root of x plus 2, that's this equation here, the line y equals x, that's this equation here, the line y equals 0, which is the x-axis, and we're going to revolve this region around the x-axis. So, once again, in order to only use one integral, we're going to use parallel rectangles. If we come in here with horizontal rectangles, we can actually solve this using one integration. So we're going to integrate from A to B of the radius times the height, and because these are horizontal, that means we're going to be working with y's. So the volume will be 2 pi times the integral. The y values are going to range from 0 to 2, and the radius, which is the distance from the axis of rotation to the rectangle, that distance is a radius value of y. So y times the height. Now once again, just like we had back in our area formula, to find the height of the rectangle, we're going to take the right side minus the left side. The right side is the line, which is going to be y minus the left side. Now the left side is the half parabola. However, we cannot put the square root of x plus 2 into our integral because we need to have it all in terms of y's. So we are going to have to solve for x. So I'm going to square both sides of my equation and then subtract 2. So x is equal to y squared minus 2. So the right function is the line y. The left function is going to be the half parabola of y squared minus 2. So once again, 2 pi times the integral from 0 to 2. The y is going to be the radius, or the distance away from the axis of rotation. The height of the rectangle is going to be found by taking the right side minus the left side. Now, just like with our disc and washer method, we can actually revolve regions around other lines. So I'm going to take this one region, y equals the square root of x, y equals 0, and x equals 4, which is this region right in here, and I'm going to revolve it around a couple different axes. The first one that I want to revolve this around is the y-axis. So if we revolve this around the y-axis, and we use the shell method. I understand we can use disc and we can use washer, but I want to focus on the shell method right now. So if we come in here and we use the shell method, that means that because this is a vertical axis of revolution, we need to have a vertical rectangle. So our volume is going to be 2 pi times the integral from A to B of r times h, and because these are vertical rectangles, we're working with x's. Now this point of intersection right here is going to be at the point 4, 2. So our x's are going to range from 0 to 4. So the volume will be 2 pi times the integral from 0 to 4. The radius, the distance from the axis of rotation to the rectangle, is going to be x, and the height of the rectangle is the top minus bottom. Now the top is going to be the square root of x, and the bottom is just 0. So that's how we would set this up to revolve this around the y-axis. Now, revolving it around the axis of x equals 4. So that's this line right here. We're going to revolve it around x equals 4. Once again, the rectangles do need to be parallel. So if we have a vertical axis of revolution, that means we need a vertical rectangle. If we are working with vertical rectangles, that means we are working with x's. So we're going to take 2 pi times the integral from a to b of r times h times the thickness, which is dx. So the x's, as we said before, are going to go from 0 to 4. That does not change. However, the radius, once again, is the distance from the axis of rotation to the rectangle. This is the radius. Now, in order for us to find that radius value, we're going to need to take the entire distance back to the y-axis, which is 4 units, and we're going to subtract out the value of x. Remember that when you plot points, the coordinate points x and y are always marked off of the origin. So the distance from here to the rectangle is x, which means that the distance for the radius is the full distance of 4 minus x. So the radius is 4 minus x, and then the height of the rectangle has not changed. The height of the rectangle is still top minus bottom, which is the square root of x, and then we have our differential of dx. Now, if we revolve this around the line x equals 5, so that's going to be over here. There's actually a gap in between the region that we're revolving and our axis of rotation. However, with the shell method, we don't need to make a distinction between whether it's flush up against the axis or whether there's a gap. We're going to set it up the same way. If we have a vertical axis of rotation, that means that for shell method, we need to have vertical rectangles. Vertical rectangles mean we're going to be working with x's. So 2 pi times the integral from a to b of r times h, and our thickness, the differential of x. So once again, the x values still range from 0 to 4. That does not change. The region has not changed, so the limits of integration have not changed. What has changed, though, is the distance from the axis of rotation to the rectangle. This is my radius r. Now, once again, in order to find that radius, we need to figure out how far we are back away from that y-axis. That's going to be 5 units. And then the distance from the y-axis over to the rectangle is our distance of x. So to get the radius, the distance from the axis of rotation to the rectangle, we're going to take the full distance of 5 and subtract out x. So the radius is 5 minus x. And then the height of the rectangle, once again, that hasn't changed. That goes from top to top minus bottom as the square root of x. So notice that changing the axis of rotation, it doesn't change the coefficient. All of these are going to be multiplied by 2 pi. It does not change the limits of integration. The x's all still go from 0 to 4. It doesn't change the height of the rectangle or even the differential. The only piece that it changes is going to be the radius. So that's really the only part that we have to keep track of. So if I come over here and ask you to revolve this around x equals -2, now we are rotating around the axis over here to the far left. Once again, we are revolving it around a vertical axis of rotation, which means that we need vertical rectangles. So we're still working with x's. So 2 pi times the integral from a to b of r times h times our thickness, which in this case is dx. So once again, the only thing that's going to change is the radius. The x's still range from 0 to 4. The height is still going to be top minus bottom. The differential is still going to be dx. The difference is that the radius, which is the distance from the axis of rotation to the rectangle, has now changed. Now this one's just a little bit different because we're on the left side. What I know is that in order for me to get back to the y-axis, I need to go 2 units. Once I get there, I know that I'm going to need to go x units more to get over to that rectangle. So the radius is going to be 2